Good morning everyone, welcome to my vlog. So for today's vlog, we will discuss about the indeterminate forms. The term was originally introduced by Katche students Myogno in the middle of the 19th century. What are indeterminate forms? In calculus and other branches of mathematical analysis, limits involving an algebraic combination of functions in an independent variable may often be evaluated by replacing this function by their limits. If the expression obtained after this substitution does not give enough information to determine the original limit, it is said to take on the indeterminate form. So, these are the types of indeterminate forms. First, we have 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 raised to 0, 1 raised to infinity, and lastly, infinity raised to 0. So, the form is indeterminate form is 0 over 0 form. So, limit of the form f of x all over g of x, where limit f of x is equal to limit g of x is equal to 0, are called indeterminate form of the type 0 over 0. So, consider that, example, limit x approaches to 2, limit x squared minus 4 over x minus 2, where x is approaches to 2. If we try to evaluate this by direct substitution, we get 0 over 0. So 0 divided by 0 cannot be evaluated, and this is an example of indeterminate forms. In this case, we can evaluate this limit by factoring and cancelling. So we have limit x squared minus 4 all over x minus 2, which is x approaches to 2, limit factoring x plus 2, x minus 2 all over x minus 2. So cancel out the x minus 2, then our answer is limit x plus 2, where each x is approaches to 2. The answer is 4. So we can use the L'Hospital's rule. So L'Hospital's rule is the general method for evaluating the indeterminate forms 0 over 0 or infinity over infinity. This rule states that under appropriate condition, so limit f of x all over g of x, where x is approaches to consonant. So if prime and g prime are derivatives of f and g, note that this rule does not apply to expression infinity over 0, 1 over 0, and so on. So these derivatives will allow one to perform algebraic simplification and eventually evaluate the limit. So, rules to evaluate 0 over 0 form. So first, check whether the limit is an indeterminate form. If it is not, then we cannot apply L'Hospital rule. So number 2, differentiate f of x and g of x separately. The third one is g prime of a does not equal to 0, then the limit will exist. It may be finite infinity or negative infinity. If g prime of a is equals to 0, then follow rule number 4. So differentiate f prime of x and g prime of x separately. Then lastly is continue the process till required value is reached. So say for example, limit 1 negative cos x all over x plus x squared, which is x is approaches to 0. So it is not longer indeterminate. As you can see, the answer is 0, which is the answer is not indeterminate, so you need to stop. Then if we try to continue with L'Hospital rule, which is wrong. So, on the other hand, you can apply L'Hospital rule as many times as necessary, as long as the fraction is still indeterminate. So, example, limit x squared minus 4 over x minus 2, where x approaches to 2. So, limit 2x all over 1 which is x approaches to 2, so 2 times 2 is equals to 4, which is the answer is not indeterminate. Since number 2 is limit tangent 3x over sine 2x, x approaches to 0. So you will derive those trigonometric function. So the final answer is 3 over 2, which is the answer is not indeterminate. Then number 3, same process also when using L'Hospital rule. So infinity over infinity form. If limits x plus f of x is equal to infinity, then limit g of x is equal to infinity. Then it is an indeterminate form of type 0 over 0. So example, find the limit of 5x minus 2 all over 7x plus 3. So we have limit 5x minus 2 all over 7x plus 3, which is the answer is indeterminate. So we derive those constant. So 5x minus 2 over x, then 7x plus 3 over x, then 5x minus 2x is equals to 5 minus 2x is equals to 0, then 7 plus 3x is equals to 7. So 5 minus 0 is equals to 5, the 7 plus 0 is equals to 7. And that's all. Thank you.